This presentation will be focusing on the concept of perfusion by introducing hemodynamics. We will discuss key hemodynamic concepts and their significance in the ICU setting. So let's review what perfusion means again. Remember, perfusion refers to the flow of blood through arteries and capillaries, delivering nutrients and oxygen to cells and removing cellular waste products. So in a sense, effective blood flow and letting blood do the job that it's supposed to do. Now, to explore this concept deeper, we'll be looking at hemodynamics, which describe the forces of the heart and the flow of blood throughout the body, how there are higher or lower pressures in certain areas, and that pressure is created by the amount of blood in that area as well as its container. So it's that relationship with the amount of blood to the size of the container that blood is in. And that container could be a chamber of the heart, or it could be a dilated vein or a constricted or sclerosed artery. So you can see why hemodynamics are central to our main concept of perfusion. And just a reminder, before you continue throughout this presentation, you need to have printed out the heart diagram in your course module to follow along. So here is your heart diagram that you printed out in preparation for this presentation. The first thing you will do is label the chambers of the heart as well as where the blood is flowing out of the ventricles to the system or to the lungs. Pretend your patient is laying on your computer screen, so your left will be their right and your right will be their left. You can pause the slide and then restart it to check that you have labeled these correctly. Before we get into looking at specific hemodynamic measures, let's think about all of the many elements that could affect the flow of blood in someone's cardiovascular system. Obviously, the heart is going to dictate a lot of this, but also the status of our arteries, our veins, capillaries, and the nature of our blood will impact hemodynamics. So for example, how strong is the pump or the heart? How much fluid is getting pumped around? What does the fluid look like? What's going on with our vasculature? So go ahead and take a look at all of these factors on the slide and pause the presentation if you need to review how could certain elements affect hemodynamics. So now that we recognize hemodynamics has to do with the flow of blood and the forces impacting that flow of blood throughout the body, now let's see why we care about this. Why would it be helpful to have this information? Well, one thing we can assess by looking at hemodynamics is how well the heart is pumping. Because we're talking about flow of blood, we can see how well the heart works or how hard it can squeeze, how strong that heart muscle is, by actually measuring how much blood is getting pumped out of the left ventricle. Remember, the left ventricle is the powerhouse. The left side of the heart pumps blood to the systemic circulation, so it's important to see how well it's doing its job. So we want to measure how well the heart is pumping, how strong that muscle is. So how do we do this? How do we measure it and what do we call it? Well, one way to measure how strong the heart is called an ejection fraction. And that name is kind of self-explanatory. It's the fraction of blood that was in the left ventricle that was ejected during systole or during contraction. So remember, the left ventricle doesn't completely empty out every time it squeezes during systole. A little bit of blood is left behind, and that's normal. However, if too much blood is left behind, what does that mean? Well, the ventricle didn't squeeze hard enough to get enough blood out. So ejection fraction is calculated in a percentage. What percentage of blood that was in the ventricle was left behind when it squeezed? How do we measure this? Well, we have to look at the heart itself. With an ultrasound, or what's called an echocardiogram, the ultrasound technician looks at the heart and can take pictures and calculate the amount of blood in a ventricle before systole and then after systole, and then calculate the percentage of blood that was left behind versus the amount of blood that left the heart. So ejection fraction is that percentage of blood that left the left ventricle. So in addition to ejection fraction, we can also measure what's called a stroke volume. So the key word here is volume. Thus, we aren't measuring a percentage anymore. We're measuring the amount of blood in milliliters that leaves the left ventricle with each squeeze during systole. Note that stroke volume is the word here. So it's one stroke or one squeeze of the left ventricle that we're looking at. And we get these numbers using a number of different devices. We can still use the echocardiogram and look at the heart itself, but we can also use a number of invasive lines such as an intra-arterial line, pulmonary artery catheter, but we'll get into those details later. Now remember, ejection fraction and stroke volume are telling us about the strength of the squeeze in the heart. This is also called contractility, and this is a key concept for you to remember, contractility. So now it's time to get back to your drawings. So looking at the heart you labeled, where would you calculate ejection fraction? Where would you calculate the stroke volume? Pause the presentation and label your heart with ejection fraction and stroke volume in the correct place. Now, here are your correct answers. Let's look at stroke volume and ejection fraction more visually here. You don't need to write or draw these images on your heart drawings because it'll get a little bit cluttered as we add in more hemodynamic measurements later. So just watch. So you can see here, we're talking about these measurements during the time that the ventricle is contracting in systole. We're taking these measurements during ventricular systole. Once that left ventricle has squeezed, it sends out a certain amount of blood. So see the red ribbon representing the amount of blood coming out with that one squeeze. We look back at the ventricle and we see that not all the blood in the left ventricle was actually pumped out. So our ejection fraction is the percentage of blood that was in the left ventricle that was now actually pumped out. Now the stroke volume is looking at that same red ribbon, that same amount of blood that was pumped out of the left ventricle. But instead of giving it a percentage and comparing it to what's left over back in the ventricle, we're actually measuring the amount of blood in milliliters. So we just looked at the strength of the heart muscle, or contractility, with one squeeze of the left ventricle. And this is useful, but wouldn't it be helpful to see how much blood our left ventricle is able to get out to the system over a whole minute? Well, we can do just that by taking that stroke volume, that amount of milliliters pumped out with each squeeze of the left ventricle, and multiplying it by the number of stroke volumes in a minute, you get the total amount of blood pumped out of the left ventricle over a minute. So how do we know how many stroke volumes there will be in a minute? Well, that's the heart rate. So what do we call these values that give us the amount of blood getting pumped out of the ventricle each minute? This is cardiac output, and it's an actual volume of blood, just like our stroke volume, that leaves the left ventricle over a minute. So how do we measure this? Well, it's those invasive lines again, the intra-arterial catheter and pulmonary artery catheter, but more details to come on these. So if cardiac output is a total amount of blood pumped out over a minute, this is helpful. But let's say we have an 80-pound woman and she has a cardiac output of 4.5 liters in a minute. And then we also have a 350-pound man, and his cardiac output is 4.5 liters in a minute. I'll tell you that both of these numbers technically fall within the normal range for cardiac output. But does this sound okay to you? Someone over 4 times the size of our little 80-pound woman probably needs more blood than 4.5 liters to pump to that larger body. So this is where cardiac index comes into play. And cardiac index uses that same cardiac output number, but then takes into account the size of the person or their body surface area. So which number do you think is more useful to us, cardiac output or cardiac index? It's cardiac index, because now we see if 4.5 liters was really enough blood for a 350-pound man. So back to your heart drawing. Go ahead and label where we would measure cardiac output and cardiac index. Pause the slide and then restart it to check your answer. So here's your answer. Notice it's right next to your ejection fraction and stroke volume. We're using the same numbers from stroke volume to calculate cardiac output and cardiac index. So now let's take a closer look at cardiac output and cardiac index. Again, no need to draw these extra illustrations on your heart paper. Now remember, again, we are still looking at the numbers from when the ventricle is contracting during ventricular systole. So really, there's not a whole lot of new information to learn here. All we're really doing is looking at that stroke volume and multiplying it by the number of stroke volumes in a minute, or the heart rate, thus calculating the larger amount of blood being pumped out over a minute, giving us a number of liters per minute. For cardiac index, we are just adding one more step, dividing that same number of the patient's body surface area to give us a liters per minute per meter squared. So how well is the heart pumping? Notice I'm asking the exact same question again and again. There are still other ways we can measure how effectively the heart is pumping. Now, aside from measuring how much actual blood volume was pumped out of the left ventricle with each beat, which remember is our stroke volume, or the percentage of blood that was pumped out of the left ventricle, which is our ejection fraction, or even the amount of blood pumped out of the left ventricle over a minute, which is our cardiac output, or even making that cardiac output more specific to the size of the person, which is our cardiac index, there is still more that we can look at to see how well that heart is pumping. So instead of looking at how much blood was pumped out, what about how much blood was left behind? So a good pump not only pumps a lot of blood out, but it doesn't leave a lot of blood behind, kind of similar to what we look at with ejection fraction. So when we measure what's left behind, instead of looking at a certain amount of blood or a percentage of blood left behind, kind of like when we look at ejection fraction, we look at pressure. So we could say that if there's a lot of blood left behind, that would create a lot of pressure. So lots of blood volume would translate to lots of pressure. Less blood volume would be less pressure. So my next question for you is, where would this blood back up? Well, just go backwards from where the blood was supposed to go. So if you look at this picture of the heart, the blood is going to back up from the ventricles to the atria. So now we've been talking a lot about the left ventricle lately, but remember we have two pumps. We have the left ventricle and the right ventricle. So we would like to assess how well both sides of the heart work. So since all of the other values we're looking at the left side of the heart, the ejection fraction, stroke volume, cardiac output, cardiac index, we can now look at the left and the right sides because we can measure pressure in both atria. So what does this look like? Remember, we're looking at pressure in millimeters mercury in the right and left atria. So beginning with the right side, we call pressure in the right atrium right atrial pressure, which makes sense. However, you will see a different name used much more commonly in the ICU, and this is central venous pressure. Now, why is that? Well, look at the red star to the right of the slide. That is the right atrium, and very technically and specifically the right atrial pressure. However, remember that in order to get these pressure readings from our patients, we have to stick something in there. We have to put a catheter in the right atrium. And while there are devices that do this that we'll talk about later, we'd like to avoid sticking a tube into somebody's heart if at all possible. So instead, we use a central line, which is pretty darn close to the right atrium. Remember, central lines are called central because they're very close to the center. They have access to the vena cava. We call the pressure in that area central venous pressure, or CVP, and we can use it to very closely estimate the amount of pressure in the right atrium. Now, why is the CVP so similar to the RAP, or right atrial pressure? Well, are there any valves between the superior vena cava and the right atrium? No. So the pressure in the right atrium will translate back to the central venous pressure very easily. So bottom line, there is not typically a significant difference between CVP and RAP. We tend to use these numbers for the same purpose. Now, what would cause a lot of pressure in the right atrium? Well, we talked about how if the right ventricle is not pumping well, then blood would back up into the right atrium. But is there anything else that might cause high pressure in the right atrium? What about fluid coming from the other direction, not from the ventricle, but from the system? So a patient who is hypervolemic or fluid overloaded will have a whole lot more blood coming back to the right side of the heart from the system than a patient who is normal volemic or hypovolemic. So a high CVP or RAP could mean two things: a bad right ventricle, a bad pump, or hypervolemia, or potentially both. Now, what about a low CVP or a low RAP? Well, you might be tempted to say a really good pump that cleared all the blood out of there, but this is typically not the case. Rather, a low CVP or a right atrial pressure is most commonly due to hypovolemia or not enough fluid in the system coming back to the heart in the right atrium. So a low CVP or right atrial pressure typically means one thing: not enough fluid coming back to the heart. So we're really just looking at that one direction. Now, this could be caused by a lot of different things, but the most common cause is hypovolemia. However, if you think about it, a patient who is very vasodilated systemically is pooling their systemic blood in the system and not getting it back to the heart efficiently, causing a low CVP or a low RAP. So coming back to your heart drawing, where would you label CVP and RAP? Pause the presentation to label your heart and then restart to check your answer. So here we have your CVP and RAP. Remember, we use them for the same reasons, to assess right ventricular function and to assess fluid volume status. So our normal ranges are the same for both CVP and RAP. Also, you see the word preload here at the top. Remember how ejection fraction and stroke volume and cardiac output and cardiac index, those all measured contractility. Well, CVP and RAP measure what's called preload. Now, preload can be defined in a few different ways, but essentially it describes the amount of ventricular stretch before the next contraction. Now, this might be a little confusing. Why are we measuring pressure in the atrium to describe ventricular stretch? But think about when the ventricle stretches. It stretches when it's getting filled up with blood. We're preloading the ventricle to get ready to contract, in a sense. So what preloads the ventricle? Well, the pressure in the atrium. Therefore, high pressure in the atrium will translate into a high preload for the ventricle, and low would translate to low. So whenever you look at any atrial pressure, right or left, you are referring to preload. Remember this term. So let's take a quick quiz. Which of the following relates to the concept of contractility? Select all that apply. Pause the slide and consider your answer. The correct answers are ejection fraction, cardiac index, and stroke volume. Remember, all of these hemodynamic values are measuring how hard the heart can squeeze by measuring how much blood is getting pumped out of the left ventricle. Next question. Which of the following relates to the concept of preload? Select all that apply. Pause the presentation and consider your answer. The correct answers are right atrial pressure, central venous pressure, and ventricular stretch before systole. Remember, any atrial pressure is categorized as preload, and these atrial pressures are preloading the ventricles before they contract. So we've talked about contractility, or the amount of squeeze, the force of the heart muscle that it creates when it's in systole. And we've talked about preload, the ventricular stretch before systole, which translates into pressure in the atria about to fill those ventricles. Notice we have not talked about the left atrial pressure yet. And remember that this is preload for the left ventricle. But in order to get this left atrial pressure number, things get a little more complicated since we can't use a central line anymore. It doesn't terminate in the left atrium. So we will review left atrial pressures in class when we talk about these more complex devices that can gather this information for us. So now after contractility and preload, the last category of hemodynamic values is called afterload. And this refers to how much work the heart has to do or how much resistance there is on the other side of the ventricle. When we talk about how much work the ventricle has to do, we're really looking at the amount of resistance the ventricle has to overcome when it squeezes. So remember again, we have two ventricles. So each ventricle is up against different types of resistance coming from two different areas. The left ventricle is pumping into the system, so it has to pump hard enough to open the aortic valve, and then any systemic resistance like systemic vasoconstriction could increase afterload for that left ventricle. Now the right ventricle is pumping into the pulmonary circulation, so it has to pump hard enough to open the pulmonic valve, and then any resistance in the lungs, like pulmonary hypertension, for example, could increase the afterload for the right ventricle. So we call these measures pulmonary vascular resistance for the right ventricle on the right side, and systemic vascular resistance for the left ventricle. So if the PVR, the pulmonary vascular resistance, is high, the right ventricle is having to work even harder, thus increasing your cardiac workload. And if the SVR is high, now the left ventricle is having to work harder, again, increasing your cardiac workload. So this image on the right gives us an example of how preload relates to afterload. The right atrial pressure is given as an example of preload. Just remember that there's also a left preload that's not shown here. And the SVR is given as an example of afterload. And again, just remember that there's also an afterload on the right, which is the PVR, but that's not shown here. But you can kind of see one is filling up and one is resistance against the ventricle. So back to your heart drawing, right where SVR and PVR would be found on this image. Pause the presentation and then restart it to check your answer. So here's where your SVR and PVR would be. Just note that each of these has arrows pointing back to the heart, showing that the direction of pressure is actually against the heart or against the ventricle. So SVR and PVR are measured in dynes per second per centimeter to the -5th power. Now, while it's not essential that you memorize this unit of measurement, just notice that a normal SVR is much higher than a PVR. So why do you think this is? Now remember, you have arterial pressure, your blood pressure in your arterial system, and that's what your left ventricle has to overcome. All of that blood pressure is afterload in a sense. It's pressure that your left ventricle has to overcome to get blood out of the heart. So we've talked a lot about different hemodynamic measures, but what are we forgetting about that we already know and that we don't need any invasive lines to measure? What else tells us about movement of blood throughout the body and forces of contraction in the heart? Our blood pressure, and specifically our mean arterial pressure, and this is the average pressure in our arteries. This is essential for tissue perfusion. And we get this number by taking our systolic blood pressure and adding that to 2 times our diastolic blood pressure, and then dividing that by 3. A normal MAP is 70 to 105 millimeters mercury. Just note that you might see orders to keep a patient's MAP above 60 or 65, depending on their pathology, and a MAP of 60 is said to be enough to maintain tissue perfusion. So just remember, in our very sick patients, it may be safer or more realistic to keep a MAP of 60 or 65. So in these 2 monitors here, you can see where to find the MAP in your patient. The monitor actually calculates it for you automatically. And so on the top, you can see we have a patient with a MAP of 79, and the bottom patient here has a MAP of 80. So there are still a few hemodynamic measures that we haven't discussed yet, and this is because they require placement of a very invasive line, specifically a pulmonary artery catheter. And this line is also considered a central line, but unlike the other central lines you're familiar with, it's actually inserted into the heart itself. It's threaded through the right side of the heart and up into the pulmonary valve, so we are able to get the actual right atrial pressure. We can even get a pulmonary artery pressure, and we can get what's called a PAOP, or the pulmonary artery occlusive pressure, also known as the PAWP, or pulmonary artery wedge pressure. We will get into these details in class, but begin to think about why these pressures might be helpful, and also what kinds of risks there might be when you put a catheter into somebody's heart. So this is the end of your hemodynamics presentation. Remember to bring your heart diagrams to class so that we can add further hemodynamic measurements as we continue to discuss hemodynamics. Thank you.